coils of his very successful battery charger, which is COP equals 13 when operating at 24 volts. That is, the output power is 13 times greater than the input power needed to make it operate. If you decide to build one of these devices, then please understand clearly that you do so at your own risk, and you, and only you, are responsible for your actions. This presentation is for information purposes only. Ron's device is much more powerful than the average battery charger in that it has 15 coils and it performs most impressively. Here's a photograph of it rotating at high speed. The magnets embedded in the rotor can't be seen because they're passing by too fast. This is not a toy. It draws significant current and it produces substantial charging rates. Here's how Ron chose to build his device. Interestingly, considering the major magnetic effect that aluminium has, the rotor is constructed of aluminium, which in Ron's experience indicates that it is a very suitable material for the rotor. The rotor has 6 magnets inserted in it. These magnets are spaced 60 degrees apart, with the north poles facing outwards. The magnets are ceramic types, 47 by 22 by 10 millimeters in size, and they're used in pairs, so there's a total of 12 magnets in the construction. The magnets are paired together to match their magnetic strengths as closely as possible. Having bought several spare magnets, Ron graded them all in order of their magnetic strength, which varies a bit from magnet to magnet. Ron did his grading using a Gauss meter, but an alternative method is to use a paper clip of about 30 millimeters long and measure the distance at which one end of the paper clip just starts to rise off the table as the magnet is moved down towards it. Having graded the magnets in order of strength, Ron then took the 12 strongest magnets and paired them off, placing the weakest and strongest together, the second weakest and the second strongest together, and so on. This produced 6 pairs of magnets with fairly closely matching magnetic strengths. The pairs of magnets were then glued in place in the rotor using superglue. This is the position of the magnets, and this is a photograph of the completed rotor. The clearance between the magnet faces and the coils is about 6 millimeters when they're adjusted for optimum performance by sliding the coils nearer to or further away from the rotor. The coils are unusual in that they have 5 separate strands of wire in each coil spool. The strands of wire are twisted together before the coil is wound, effectively making each coil spool a 5-coil combination of electromagnet, transformer, and pickup coils. There are 3 of these coil spools, each being about 75 millimeters long and wound with 5 strands of number 19 American wire gauge or 20 standard wire gauge wire. That's a wire of 0.912 millimeters diameter. The coil spools were made from plastic pipe of 7/8 inch diameter. Now that's 22 millimeters. And Ron drilled out that pipe to an inner diameter of 3/4 of an inch, which is 19 millimeters. And that gives a wall thickness of 1.5 millimeters. The end pieces for the coil spools were made from 3 millimeter thick PVC, which was fixed to the plastic tube using plumber's PVC glue. Before winding the coils, the 5 wires were twisted together by clamping the ends of the wires together to form a 120-foot long bundle of wires, which were stretched out and kept clear of the ground by passing it through the openings in a set of patio chairs. A battery-powered drill was attached to one end, and operate it until the wires were loosely twisted together. Doing this tends to twist the wires together more tightly at the end, leaving the set of wires looser in the middle. So the procedure was repeated, twisting the other end of the bundle. In passing, the drill turns in the same direction for doing that. The twisted wires are collected on a large diameter drum and then used to wind one of the coil sets for the charger. This is a picture of one of the coil sets used. You have the end piece, which is shaped like this, with two holes drilled in the bottom where a base piece will be screwed to the two ends of the coil. The wire is wound round the coil. It starts in the middle, coming out near the center, and it finishes up at the outside edge, coming out there in the end piece of the coil. The individual wires are wound side by side along the length of the pipe. Then a layer of paper is attached round them, and that makes it easier to wind further layers. And the layers are repeatedly done until the spool itself is full of wire. The unit itself, when it's completed, the coil base itself, when completed, is actually bolted to 18mm thick MDF base. It is easy to wind a coil with wire this thick, and the end of each full layer of winding, a layer of paper is attached, and that layer makes the next layer of wire even easier to wind because you can see it much better. Ron's constructional work is of very high quality, and he uses the equipment shown in this photograph. He has the reel of wire with the ends already attached, bolted to a turning handle. He has a counter on it, but as he already knows the length of wire he's going to wind, that's not important. The winder is clamped to his drill press. There are two completed wire coils, and they in the base have got a slot which allows the coil to be slid closer to or further away from the actual rotor. The twisted wire is wound onto a large spool, and that is then used to feed wire to the actual coil wind. The three coils produced this way were then attached to the main surface of the device. There is an adjustable gap between the coils and the rotor so that the optimum spacing can be found. The magnetic effects are magnified by the core material of the coils. This core is made from lengths of oxyacetylene welding wire, which is copper coated. The wire is cut to size and coated with shellac to prevent energy loss through eddy currents circulating inside the core. The coils are positioned at equal intervals around the rotor, and so are 120 degrees apart. The end pieces of the coil formers are bolted to a base plate which has slotted mounting holes, which allows the magnetic gap to be adjusted as shown here. This is the rotor with the 6 pairs of magnets glued into it. The red line indicates the glue joint. The 3 coils are at 120 degrees apart, and they have a slot in the base, 4 slots, 2 on each side, so that the position of the coil can be adjusted. Now, the 3 coils have a total of 15 identical windings. One winding is used to sense when the rotor magnets reach the coils during its rotation. This will happen 6 times during each rotation, as there are 6 evenly spaced magnets in the rotor. When the trigger winding is activated by the magnet, the electronic circuit powers up all of the remaining 14 coils with a very sharp pulse which has a very short rise time and a very short fall time. The sharpness and brevity of this pulse is a critical factor in drawing excess energy in from the surrounding environment. The electronic circuitry is mounted on 3 aluminium heat sinks, each about 100 by 100 millimeters in size. That's 4 inches square. 2 of these plates have got 5 BD243C NPN transistors bolted to them, and the third has 4 BD243C transistors mounted on it. The metal mounting tab of the transistor acts as its heatsink, and that's why it's bolted to the aluminium plate. The transistor looks like this. You've got the base at one side, the collector in the middle, and the emitter on the other side. And as I've already said, the collector is internally connected to the mounting tab. Mica washers are placed between the transistors and the aluminium plate. You can see them there. And the reason for doing that is because this allows heat transfer between the transistor and the aluminium plate, but it doesn't allow electrical transfer, and this avoids unwanted connections being made to the other electronic components. Ordinary hardware store screw connector blocks are used to make the wire connections to this particular construction. The circuit used for this device is simple, but as there are so many components involved, the circuit diagram is split into parts which fit on a page. Diagrams of this kind are usually drawn with just one wire going to the top of the battery, which is being charged, but it needs to be understood that drawing it that way is just for convenience, and better performance is achieved if each charging circuit has its own separate wire going to the battery being charged, as shown in section 1 here. The charge from this blue coil, for instance, goes out through these blue diodes and through the blue separate charging wire to the 12-volt battery which is being charged. There are 3 diodes placed side by side here, as that lowers the resistance of the diodes and raises the current carrying capacity. But this is the first part of the circuit. The coil shown in grey is the trigger coil, and when a rotor magnet swings past it, that develops a voltage in the coil. That's passed through a car 12-volt bulb, on through a 100 ohm resistor, and on through a 100 ohm wire wound variable resistor, and that forms the trigger line, which is used to power all of the transistors through their 470 ohm base current resistor. So that's the first section of the circuit. The second section is almost identical. You've got 5 separate coils powered by 5 separate transistors, each of which are fed by that same trigger line, each being fed through a 470 ohm resistor. And the third section is identical to the second section. You've got 5 transistors, all driving output voltage pulses which go through triple diodes and out to the battery which is being charged. This looks like a fairly large and complicated circuit, but it actually is not. You'll notice that there are 14 identical circuit sections, and each of these is quite simple. This is a very simple transistor circuit. When a magnet passes the coil, the grey trigger wire goes positive and the transistor gets switched on hard, powering the coil. The coil is connected through the red wire to the driving battery, and the trigger pulse is very short, and so the transistor switches off almost immediately. The sudden switching off of the transistor causes a major back EMF voltage spike to build up across the coil. This pushes the transistor collector voltage up high, and if it were not for the connection to the battery, which limits the voltage, then the voltage would reach several hundred volts. However, as the voltage passes the voltage of the charging battery, current starts to flow into the battery being charged. The higher the voltage goes, the greater the current flowing into the battery. The coil has limited back EMF power, so it can't get to too high a voltage, as the current flow into the battery limits it. That means that you don't want to have the circuit running if the battery being charged is not connected. You'll notice that the current fed to the charging battery goes through 3 diodes instead of just one. This is good practice, as it lowers the resistance between the transistor and the battery. It raises the current handling capacity of the composite diode, and then, as already mentioned, each coil has its own charging wire going to the battery. The only other part of the circuit is the section which generates the trigger signal and which switches all of the transistors on together. The bulb has more than one function, in that as well as limiting the current, it also glows dimly, which is a very useful indication of the operation of the circuit as a whole. The trigger circuit then feeds current to every transistor through their base resistors. There are various ways of constructing this circuit. Ron shows different methods. The first is to use strips of Paxillan panel above the heatsink in order to insulate the components. The second method, which is easy to see, uses thick copper wires held clear of the aluminium plate, and that provides a clean, low resistance, secure mounting for the components as shown here. These are the main wires which the components are attached to. They're welded or soldered directly in mid-air, and there is no actual connection board used in this method. The components are all welded together, soldered together. It's important to realize that the collector of a transistor is connected internally to the heatsink. Now, you definitely need to use mica washers between the metal heatsink plate and the metal transistor tab. In this photograph, it looks as if metal bolts are being used to attach the transistor to the aluminium plate. That's not the case, because the metal bolts go into plastic T-nuts, which prevent any electrical connection. The circuit board is connected to the rear of the main unit, as can be seen in this photograph. There's the circuit board of that construction, and it is bolted to the actual side of the charging unit. The other things seen in this circuit are the variable resistor with its knob for adjustment, the bulb, which surprisingly is mounted upside down, and the back of the rotor, where the bearing is bolted securely to the vertical member there. Although the circuit diagram shows a 12-volt drive supply, which is a very common supply voltage, Ron usually powers his charger with a mains operated power supply, which draws a pretty trivial 43 watts, and he charges his 24-volt batteries using the circuit. Ron uses a very neat shears arrangement for cutting exact lengths of welding rod, which are then grouped together to form the core of one of his 5-strand coils. That shearing arrangement is very neat. The back aluminium plate here stops the wire as you slide it through the shears, which are held by the bench vise. When the cut is made, the piece drops into the plastic container, and that method gets all the pieces the same length. It's very quick and easy to do. Now, the pieces that collect in the plastic container are ready then for coating with either clear shellac or clear polyurethane before use in the core coils. Now, experience is particularly important when operating a charger of this kind. The 100 ohm variable resistor should be a wire wound type, as it has to carry significant current. Initially, the variable resistor is set to its minimum value and the power is applied to the circuit. This causes the rotor to start moving. As the rate of spin increases, the resistance is gradually increased and a maximum speed will be found with the variable resistor in roughly the middle of its range. That is at about 50 ohms resistance for the variable resistor. The next step is to turn the variable resistor to its minimum resistance setting again. This causes the rotor to leave its previous maximum speed of about 1700 rpm and increase its speed to about 3800 rpm. This is probably fast enough for all practical purposes, and at this speed even the slightest imbalance of the rotor shows up quite markedly. So to go any faster than this requires an exceptionally high standard of constructional accuracy. Please remember that the rotor has a large amount of energy stored in it at this speed, and so it is potentially very dangerous. If the rotor breaks, or if a magnet comes off the rotor, that stored energy will produce a highly dangerous projectile. That is why it's advisable, although it's not shown in the above photographs, to construct an enclosure for the rotor. That could be a U-shaped channel between the coils, and that would catch and restrain any fragments if anything should break loose. If you were to measure the current during this adjustment process, it will be seen to reduce as the rotor speeds up. This looks as if the efficiency of the device is rising. That may be so, but it's not necessarily a good thing in this case, where we want to produce radiant energy charging of a battery bank. It has been shown that serious charging takes place between 3 amps to 5 amps or more current draw at the maximum rotor speed, and not at a miserly 50 milliamp current draw, which can be achieved but which does not produce good charging. The power can be increased by raising the input voltage to 24 volts or even higher. Some people operate at 48 volts rather than 12 volts. The device can be further tuned by stopping it and adjusting the gap between the rotor and the coils, and then repeating the startup procedure. The optimum adjustment is where the final rotor speed is the highest. These notes are at www.freeenergyinfo.com/Pugh.pdf.